crop this. So I call this lesson 6.45. So we already did 6.3a, 6.3b with 6.4a, and then 6.4b, and this is 6.45. If that's not confusing, I don't know what is. All right, so we have the fundamental theorem of calculus that tells us that the integral from a to b of f prime of x dx is f of b minus f of a. What if we solved for f of b? What would f of b equal? Can you get that by itself? What do we need to do to get that by itself? Add f of a. Not f of x, f of a. F of a. I'll tell you the page in a second. Right now we're just kind of thinking. So now that we've isolated f of b, this equation, right, this really, it's because I'm recording. I can't do anything right when I'm recording. I have to make every video twice. Okay, so all we did was add f of a to this side. So now we have f of b equals f of a plus an integral. So this is called start plus accumulation. So what this equation tells us is that we could calculate a value of a function, like I could calculate f of 5 for a function if I know a start value, like maybe I know f of 1, and then I just need to accumulate the change from 1 to 5 of f prime of x dx. So this allows us to calculate a particular value if we know a start value, and then we can, and the derivative. We need to know f prime, because then we can just integrate f prime to get how much it's changing. All right, so this is in your book on page 151, start plus accumulation, about near the bottom. Okay, so let's do that number 14 and number 15 at the bottom of the page. If f prime of x is 3x squared plus 3, and we know that f of 0 is 4, we can calculate f of 2. So f of 2 would be, well, we're starting at 0, and we know that value, plus we're going to do the integral from 0 to 2 of f prime of x dx. So I just wrote it out like the way that that formula looks in the box. But now we need to fill in the things that we know, right? So we're trying to calculate f of 2. We know f of 0 is 4. And our integral is of 3x squared plus 3 dx. We probably could have just written that first, but I wanted to make it look like the formula in the box before we started. So the 4 is just going to stay. The integral of 3x squared is x to the third, right? It's nice when it has the right coefficient. And then plus 3x, and we're evaluating it from 2 to 0. When I have a start here, I kind of like to put a beginning of what I integrated so that I don't do something weird with the 4, because it really is just this number 4 plus my integral. So if we evaluate it, we're going to sub into, and then we need to subtract 0 to the third plus 3 times 0. Love it when we get to subtract 0. So 4 plus 8 plus 6, 18, I think. I think it's 18. Because that's an 8, and that's a 6. 4 plus 6 is 10, plus 8 more. Four is the start value. So like the function, if we thought about a graph at 0, the function had a height of 4, and we're wondering what the height of the function is when x is 2, and taking the integral of the derivative is giving you that amount that it changed, and the amount that this one changed by is 8 plus 6, 14, so it went up by 14. So we found that because we integrated the derivative, it gave us how much f changed, right? Because these two things sort of undo each other, right? So does that make sense? Kind of interesting. And it was called start plus accumulation. It comes up a lot. Let's try the next one. If an object's velocity is given by v of t equals 2 to the power of 3t squared minus 5. We're going to have to use a calculator for this. Were you like panicking when you looked at what we need to integrate? We're definitely going to use a calculator for this. So s of 2 is what we want to calculate. So it's our start value. So s of 1 is 8 plus our accumulation. So what integral are we doing? We're doing the integral from 1 to 2. Yeah, so we're using s of 1 as our start value. So we're starting at 1 and we're trying to figure out the value at 2. So this first, the bottom bound is your starting x value, and the upper bound is the one you're trying to calculate the value for. Of 2 to the 3t squared minus 5 dt. And this integral is not one we could do by hand. Why not? Yeah, because what's the chain of that power? The chain of that power is a 6t. So unless we had a t or a 6t or a 2t or something, we would need a t here to be able to integrate that by hand. So we can just punch that in your calculator, and you can do it with the 8 the whole time. You can do 8 plus the integral of, from 1 to 2, and then just put your function in. Nope. Preserved for all time is my inability to use my calculator. And we get 24.502. Did anyone else get that? I had a hard time typing it in, so okay. S of 2 equals 24.502. Does it make sense to you that you could use something's position and its velocity to figure out where it ended up? Yeah, it kind of does make sense. If we know how fast you're going, we can figure out where you're going to end up.
Could you explain? If you're starting at 8, right?
Yeah.
And the velocity is in, what, let's just say, whatever, unit per unit of time, right?
Mm-hmm. Yeah.
Can't you just punch in the numbers for the velocity? Wait.
The thing I think that makes it tricky is like because the velocity is variable. Like we've got this velocity function. So at each moment in time, the velocity is a different number. Yeah, the acceleration is variable. Yeah.
So how come we're using the integral? Because doesn't the integral account for like the area under the curve?
Yeah, it's kind of weird to think about area, but if you think about a graph of velocity, meters per second, and if you times it by second, what is a unit of area? We multiply to get area, so we're timesing a meter per second times by a second, so we are getting units of meters. Yeah, isn't that weird? If we're thinking about a velocity function, the units of height are meters per second and the units of width are seconds. So that's a meter when we times it.
So the integral is the area under the velocity graph, right?
The
Sorry.
what's your question? Say it again.
Okay, so the integral is the area not under the position graph, right?
The
Like when you take the integral, you find the graph of the area under the velocity graph, right?
right, we have a velocity function, so its y value is a velocity, so the units on the y-axis are meters per second. Yeah. So this, if we had a position graph and our units were meters, this idea doesn't work. Like, we wouldn't integrate position to figure out a new position. The units of that would be weird, because it would be a meter second. And what is a meter second? I don't know.
It's actually
What is it? A force? Impulse. It might be something weird like that, yeah. My physics is not good. Yeah. If in a problem like this, it's probably better to just label your answer. Labeling is always a good idea because it's communicating that you know that you found what you were supposed to find. So I would probably label it. Okay, I want to go to number 29 that we skipped. But actually, I was like, this is garbage. I'm making them dig through their book to find things. So I think after this, I just put all the problems on a separate paper so that you don't have to dig through and find them, okay? So that's what this is. So it is on your books, in your book somewhere, but I've just thought let's just acknowledge the chaos and just do another paper. It's not. Okay. You should ask Mr. Blair what the meaning of a meter second is. Yeah, just ask him if it's something, because I don't know.
I don't think it. Like, what would you be measuring?
That's what I'm not sure. That's what you need to ask him is, what does a meter second measure? I don't know. Okay, so this is number 29. It was on a homework assignment, but I told you to skip it. But I just want to work through these now that we've talked about start plus accumulation. So this is very much a calculator problem because we've got an absolute value here. So we know f prime of x is the absolute value of 8 sine 10x. We want to know the integral from 0 to 4 of f prime of x. So in your calculator, you're just evaluating that. Oh, I got into a bad spot. 0 to 4. Remember where absolute value is? Do you need a calculator today? Okay, no, you're fine. Math, go over 8 sine 10x. Make sure that you're in radian mode for calculus, especially if you're in physics and you go back and forth. It might take a minute. Sometimes integrals take a while for the calculators to crunch. Yeah, it doesn't always process instantly. It's complicated. Did we get this? Okay. Just Google it. I'm sure you can find info on it. I don't know because I'm not a computer person. So what 2 correct answers would be accepted for this? Yeah, both 20.533 and 20.534 would be acceptable. Okay, so now we have more information. If f of 0 is 3, what is f of 4? Can you figure that out? Yeah, f of 4 is just going to be 3 plus that integral that we just did. No, not, yeah, 0 to 4. Yep, because this is f of 0, right? So our integral needs to start at 0 because this is f of 0. So our integral starts at 0, goes up to 4 of f prime of x dx. So it's 23.533 because we just need to add 3. A lot of times start plus accumulation problems are calculator active, so you often are just evaluating the integral in your calculator. It's possible it's not. There's ones we can do by hand, but a lot of times it is. Last year in the free response, they had a start plus accumulation calculator problem for one of their free responses. Okay, so I want to just talk a little bit more about particle motion. So this is not on your paper. So we need to go back to page 150. Not perfect process. Back to page 150, we want to look at example 9. These were the ones where we actually found the area. So we're going to do this one, and then we'll go back to the pink paper that I handed out. So we've got a position function this time, negative 1/2 t squared plus 4t minus 3. We want to find the displacement of the object from 1 to 4. Do you remember what displacement is? Yeah, where it started. So x of 4. Oh, whoops, I put my parenthesis in a weird spot. Displacement is just like how did your position change? So it's where you ended at, subtract where you started. X of, oh my gosh, we're starting at 1. X of 1. And I think let's just use our calculator to crunch that because we've got a quadratic with a. This is page 150. It's number 9, kind of near the bottom. Okay, displacement of a particle is end position subtract start position, and just crunch it in your calculator. You can do it this way if you want. Negative 1/2. Do you remember the trick of putting the function in your Y menu, going back to your screen and doing, not calculate, clear, F, or do Y1 of 4 minus Y1 of 1. So you can let the calculator evaluate it if you just type the function in. So again, my function is in my Y menu. I go back to my main screen. Alpha is where you can get the names of the different equations. And then just hit enter, and it will crunch it. So 9/2. Just got that out of my calculator. Okay, let's find the velocity equation next. If you have position, how do you get velocity? Take the derivative. So this will be negative t plus 4. Okay, we're going to graph a sketch of the velocity. Negative t plus 4 is, and the scale on this is kind of funky. Okay. All right, so now we want to find the integral from 1 to 4 of the velocity, not from 0 to 4, from 1 to 4. So it's this triangle right here. The height of that triangle is 3. It's a triangle, so it's half. And the base of that triangle is 3, 4.5, or 9/2. Okay. So here's something to get out of this. For particle motion, and I have it on a sheet that I'm going to give you because we're killing trees today. If you want to know the displacement, I think is it at the bottom of your page? The answers to part A and part D are the same. So if you want to know something about the displacement, and you know the velocity function, it's the integral of the velocity for those bounds. Like displacement from A to B, it would be the integral of the velocity from A to B. If you want to calculate the displacement, like we did here, but maybe you don't have, like we calculated displacement using the position function, which is easy enough. If you have a position function, do some subtraction. But if the thing you have is the velocity function, you can just integrate the velocity with those bounds. We already know that, I guess, that position is the integral of velocity. Instead of finding the general position function and doing the substitution, this just takes care of that all at once by using the bounds. It's doing the substitution for you, right? So normally you would calculate, maybe integrate without the bounds, get your function, and then you would be subbing in. This just does it, boom, one shot. The subbing in is right there. Okay.
So you could say that displacement is equal to like x minus x minus, sorry, x,
Yeah.
xb minus xa.
Yes.
So like yeah.
Yes, exactly. Exactly. And that's exactly what we did here, was that subtraction. Yeah. Okay. All right. So back to the pink paper. This was the homework problem that I told you we were going to eventually do, and we're going to do it now. So this number 30, we are going to use calculator to calculate, and then number 31, the one below it, we'll do without calculator. So if an object's acceleration is given by the function cosine t squared, and we know that the velocity at time 1 is 5, can we find the velocity at time 3? Yeah, because velocity is as acceleration is the derivative of velocity, we can think of this as start plus accumulation. It's our starting velocity, whoops, v of 1, starting velocity plus the integral from, what are my bounds? 1 to 3 of acceleration. And I'm going to write it this way. You can put in the acceleration, but I'm going to just write it. If we're trying to figure out a velocity at a particular time, we can use a starting velocity plus an integral of acceleration. So v of 3 is 5 plus, and we're just going to use our calculator to do this integral, because it's not one we could do by hand, because we would need a chain with a t, and we don't have that t. So we got to do it in our calculator. $4.798. So it's actually slowed down a little bit, right? It started at a velocity of 5. And a cosine function is definitely going to be something that's, if your acceleration is by a cosine function, it's going to be negative sometimes. So this is just a spot where it had slowed down a bit. And that would be in units of, this is a velocity, so this would be in units of feet per second. Okay, so let's try, so this next problem, number 31, we're going to do a lot of like just reviewing different parts of particle motion. So if you have your particle motion reference sheet, you can look at it, but I have a new particle motion reference sheet for you that has the integral stuff on it. I don't want to give it to you yet though, because we're going to try to figure some stuff out, but then I'll give it to you. All right, so we have a position function, t to the third power minus 3t squared plus 1 represents the position of a particle. We want to find the velocity equation. So we need to differentiate. Yes, so the velocity function is 3t squared minus 6t. Okay, next part, we want to find the acceleration equation. Yep. taking the derivative again. Okay, our next question is, can you find the velocity at time 1? Easy peasy. Velocity at time 1 is 3 times 1 squared minus 6 times 1 is -3. Yeah, remember that speed is the absolute value of velocity. So speed equals the absolute value of the velocity of time 1, which is +3. That wasn't too bad so far. I don't know what's next. Find the velocity. Oh, we already did that. Didn't we already do C and D? Okay, we're on E. I don't know why. Whatever. Okay. When is the particle's velocity decreasing? So we have our velocity equation. It was 3t squared minus 6t. So if we want to know when the velocity is decreasing, what are we thinking about? Velocity decreasing. But it's not velocity negative, it's velocity decreasing. So we need to think about acceleration negative. Yeah, it's not asking when you're going backwards, it's asking when you're slowing down. Velocity decreasing. Yes. So it could be speeding up backwards. Yes. I'm so bad at particle motion. We know we're looking for where acceleration is negative, right? Okay. So here's our acceleration equation. What is our critical number of this equation? T equals 1. So let's just make an acceleration number line. Make sure you label your number lines so that you can remember what they are telling you information about. This is an acceleration number line. My critical number is 1. If I'm at numbers less than 1, this is, so like 0, for example, negative. And if I'm at t values greater than 1, like 2, for example, positive. So when is the velocity decreasing? Yeah. You can say equal or not equal, it doesn't matter, whichever, but they won't judge you on that. Okay. Time less than 1. This is the answer. All right, now we want to find the displacement. We have the position function, so then displacement is just where we started minus where we ended. I feel like it's the same numbers we just used a minute ago. Oh, look, it's right there. I just need to put the new function in. New function. +1. If you're lazy at your calculator like me and you're like, oh, I already typed in y4 minus y1, if you changed your y, you can just copy it. Thank goodness it was the same bounds or the same t values. So I got 18. I think I did say we weren't going to use our calculators though. So I guess that was cheating. We're not going to use our calculator for the integral. We're going to do our integral because it's just a polynomial, so we can do it. Okay, so that was displacement. Total distance traveled. How do we calculate the total distance traveled? It's one of your favorites, and some of you like to do it by thinking you can just plug in all the numbers, but you can't. If I want to know total distance traveled, I have to think about what direction I'm traveling, because I might go forward and I might turn around. So I need to be able to add up all these distances we're going to need the critical numbers of the velocity. We need to figure out, does this thing turn around, right? So we need to think about our velocity equation. Our velocity equation was 3t squared minus 6t, right? Okay, so 3t times t minus 2 would be our factored velocity. So let's make a velocity number line. I'm going to also include t equals 0. It doesn't really say if we're thinking about negative time or positive time. So in calculus, they usually always allow negative time. And this is a velocity number line. So we've got to think about our velocity over here. Positive? Yeah, positive. You want to know a trick? What shape is the velocity? It's a parabola. Does that parabola open upward or downward? Can you picture the parabola? It's positive, negative, positive. Isn't that kind of in some ways better than subbing in? Like a quadratic to do positive would have to be just one critical number that happens to be the vertex. But like if you had a cubic function, it could do something like this. So that's not always, like, thinking about the graph isn't always a good trick, but it kind of is for parabolas because you know how parabolas work, you know. So, okay. So we've got a turnaround time, but we're only interested in the interval from 1 to 4. So we're only thinking about like from here to here, right? So to figure out the displacement, we need to know x of 4, we need to know x of 2, and we need to know x of 1. I kind of wrote it backwards, but those are the 3 spots we need to think about. Where did it start? Where was it when it turned around? Where did it end? And these are based on the position function, not the velocity function. If we subbed this into the velocity, we'd get 0. 1 minus 3 plus 1. This is negative 1. That one is negative 3. Somebody should really be checking this. 64 minus 48 plus 1. So I think when you're doing displacement, to me, it makes sense to kind of think about if you know, like the logic of it. This is saying we started at negative 1, we went forward to 17, and then we turned around and went back. Oh, geez. Nope. Because I'm recording? Perhaps. We started at negative 1. We went backward to negative 3. It's because I wrote it in the wrong order. And then we went forward to 17. So this leg of our journey, we traveled 2 units, and then we traveled 20, right? We went 3 and 17, so 22? Is 22 our answer? Okay. Why are they listening to the Beatles? I mean, facts, but...
No, Rhapsody.
Okay, calculus Rhapsody. All right, we have 2 parts left. The first part is to find the integral of the velocity without a calculator, and then we'll do the integral of absolute value. We'll use a calculator for that one because of the absolute value. So integral from 1 to 4 of velocity is where's my velocity? 3t squared minus 6t. So if we integrate that, it is t to the power of 3 minus t to the power 2. It has a coefficient of 6, but then we're going to divide by 2, so our coefficient is 3. And we're evaluating that from 1 to 4. So 64 minus 48 minus 1 minus 1? 1 minus 3. Minus 1 minus 3. Is that right? It's 18. Compare that to your answer on part F. If we integrate the velocity between two numbers, it is the same thing as calculating the displacement. Okay, now let's do the absolute value one, and let's use our calculator. The integral of the absolute value from 1 to 4 of the absolute value of the velocity 3x squared minus 6x dx is 22. So if you want to find the total distance traveled, instead of doing all this work with figuring out where it turned around, does it make sense that the absolute value would take care of that? Because it took care of that we went backwards, and it just did the positive of that because of the absolute value. So it just treated it as finding the total distance traveled.